This is the beginning of the lecture for chapter 6, and the topic for this particular chapter is the electronic structure of atoms. And the first thing we're going to look at here is kind of relationship, which you probably talked about at some point in some other science class, probably chemistry in the past. C equals lambda nu. C is the speed of light. Speed of light. Lambda is the wavelength. And nu is the frequency of the light. So we can look at that a little deeper and say, okay, C has, it's a constant for light. It's 3.0 times 10 to the 8th meters per second, every second, 300 million meters. Lambda is measured in the wavelength, so it's the meters from trough to trough or crest to crest per wave. And the nu is how many waves pass a given point, the frequency, every second. And just to kind of clarify, sometimes I write it like this where seconds is in the bottom, or sometimes I write it like this where seconds to the -1, indicating it's in the denominator, just like that. Okay. To give us another understanding as far as we're talking about light, different kinds of light in the electromagnetic spectrum, we can state that visible light, its ballpark range, the stuff that we see, is anywhere ballpark again between like 400 to 700 nanometers. And remember, a nanometer is 1 billionth of a meter. So these are really, really small. So 1 times 10 to the -9 for nanometers. Just to give us another push, something you've probably heard of, gamma rays. Gamma rays are really, really small. This is to the 1 times 10 to the -9. Gamma is 1 times 10 to the -11 meters, so very small. And just another portion of light on the opposite end of the spectrum. These are ballpark something greater than 10 to the 3rd meters, so like a kilometer across, wave to wave. And as far as how these things travel, they all travel at the exact same speed, which is the speed of light. It's just that there's more waves or less waves at a given point. Each of these has energy, so when this hits you, it's many, many waves with a certain amount of energy. Therefore, the impact is greater as comparison to like radio waves. Okay, let's take a look at a quick little problem in our homework, number 17. Get this ready here. All right. For the first problem, number 17, what is the frequency of radiation that has a wavelength of 10 micrometers, which is whatever number you have, times 10 to the -6, about the size of a human bacterium, about the size of a bacterium. So that's about how big it is. It's 10 micrometers across. All right, so that what we can use for all of these problems here is this formula, which we just talked about, and we can apply it with some given information. This is known. They're telling us what the wavelength is, and they're asking what the frequency is. So pretty easy. Let's just go ahead and throw the numbers in. 3.0 times 10 to the 10th meters per second is equal to 10, and I'm just going to leave it the way they wrote it. I'm not going to change it around. 10 to the -6, excuse me, meters per wave. I'm not going to write the waves in. Well, why not? Meters per wave. and that is times, again, the frequency. So these are everything I have in place. I can now isolate the variable, and if I do that, the frequency is simply 3.0 times 10 to the 13th waves per second. So that is how many waves pass a given point for every second. All right, B, what is the wavelength of the radiation as a frequency of that? So same type of problem. We know that we have 3.0 times 10 to the 8th meters per second. And this time we want to try to find the wavelength, so I don't know lambda, times the frequency, 5.50, times 10 to the 14th waves per second. And if we solve this one for lambda, we'll find an answer of 5.5 times 10 to the negative second meters per wave. And again, just isolating the variable. C, would the radiation part A or B be visible to the human eye? All right, well, we have to take a look at the different wavelengths that we have available. For this one here, we have 10 micrometers. And as far as we have to get this over into nanometers, something that we're familiar with. So to get that there, it has to get, if this unit gets smaller, the number gets bigger. So 10 micrometers, I'm not going to go through the conversion here, it would be 10,000 nanometers, which is outside of the visible spectrum, what we just talked about in the notes. This one here, I need to make this smaller by 2, so that's going to get bigger by 2. So this number here would be 550 nanometers, which happens to be kind of right in the middle of the visible spectrum. So specific what color it is, I'm not that concerned about. It's probably somewhere in the bluish range. But again, I'm not too terribly concerned about that. It's somewhere in there. I don't know. And again, that goes for part C. D, what distance does electromagnetic radiation travel in 50 microseconds? All right, so this is not necessarily something that's going to fall into that equation up there. We're going to have to look at this one a little bit differently. For this one here, we're looking, okay, we know what the speed of light is, and we have time. So we can say 3.0 times 10 to the 8th meters, I'm going to write it like this, per second. And we know the time that we have is 50 microseconds, which is times 10 to the negative 6 seconds. So seconds are going to cancel out, and you'll be left with, just run the math through, 1.5 times 10 to the 4th meters. Just running those numbers across here. So 1.5 times 10 to the 4th meters. That's how far it goes in this amount of time. Okay, so that problem is done. Let's swing that back over to our notes. And run through, that's something we have to be responsible for as far as a person, but we'll just talk about kind of like the development of a few things that we do use. And that begins with a gentleman by the name of Max Planck, a German physicist. You may have heard of him. He states energy released by atoms is really, really small. So the energy released by individual atoms is very, very small quantities. that we typically don't notice or pay attention to. Another way he refers to these things is not as quantities, but as quantums for each atom. And he develops an equation to express this, which is E equals h nu. And like any good physicist, he applies a name to this constant here as Planck's constant. And we'll give that number here in just a little, well, why not? Let's go ahead and do it right now. 6.626 times 10 to the negative 34th joules times seconds, not per seconds, but times seconds. So that energy is a constant value for Planck's constant. And this, of course, is simply the frequency of the light. And then, of course, this is the energy. So really what this develops is based upon the frequency that has a direct relationship to energy. Frequency determines the energy of light. Okay, we'll continue this off in a second lecture, which will begin after this one.